Hello.
In the full life cycle of a video, from the video being created, uploaded, processed, then distributed to the users, and eventually consumed by the end users, right? So we work on many, many algorithms, but for today, I'm just going to talk about a single project we did recently. It's a little bit technical, but I try to explain it in a user-friendly manner. Yeah, so it's called a T-ladder, TikTok's video laddering system. Right now, you probably don't know what this ladder is, but yeah, let me try to explain. Okay. So first, let's think about a very basic question: how to stream a video, right? So the simplest way to stream a video is called constant bitrate streaming. So the idea is pretty straightforward. So we basically chop a video into chunks. And the client, which has a buffer, just sequentially downloads the chunk one by one. And the client has a buffer. Whenever the buffer is full, the client will stop downloading. Whenever there's some empty space in the buffer, the client will continue downloading each chunk. Right, very straightforward. But in reality, all modern video systems are using a more adaptive way to stream the video, right? Instead of just having one quality, so the server will prepare for multiple representations for a video. So the server is dumb just for scalability. So the key logic runs on the client side, right? So the client runs something called the ABR, Adaptive Bitrate Streaming Algorithm, which will dynamically select for each chunk which quality the client will fetch based on the network condition, right? You probably can feel whenever the network is good, then you have a higher resolution video, right? So when the network condition deteriorates, then the video quality will downgrade. Right. So these multiple qualities, they form a ladder, right? You can think of when the network is good, so we climb up in the ladder, so the resolution will go up, and vice versa, right? And a little bit more details, right? For each representations, they're actually characterized by multiple encoding parameters, not just the resolution, but many other parameters like codec and many other stuff. Yes. Yes, so this is my next slide, right? So if you think about, before that, let me try to explain one thing, right? Everyone hates this store. Whenever store, we have this bad spinning icon. So why store occurs? Let me just use a very intuitive animation to show that, right? So remember that in ABR, right? So the client requested chunk by chunk. So let's say that we have a badly designed ABR algorithm, right? So here we illustrate the buffer. Let's assume that each video chunk is 1 second. So the width of each slot is 1 second, and the height is a bit rate, right? So let's say we have a very poorly designed ABR algorithm, which always fetches the highest quality regardless of the network condition. Then the video rate will exceed the network capacity, right? So then you can feel that the buffer gets shallower and shallower, and eventually the buffer becomes empty, then we have the stalls. And to answer your question, so there are actually many, many ABR algorithms. If you do a Google Scholar search, you can see there are a huge number of papers on this video streaming ABR. So some algorithms, like those old algorithms, are throughput-based. Basically, the algorithm tries to predict the network condition and make a decision. And some algorithm uses the buffer level. So when the buffer level is low, then we can intuitively lower the quality level, right? Because we have some risk of being stalled. When the buffer level is high, we can use a high resolution. And also some algorithm use the optimization approach, try to do some mathematical modeling and try to determine which level to fetch. And recently, there are some neural network-based approach. They train a machine learning model, try to predict which level to fetch. Okay, so remember I talked about this ladder, right, which consists of multiple representations. So the ladder actually determines the ABR solution space. So remember, we have multiple transcoded representations in the ladder, and these multiple representations are distributed to the clients, right? So on the service side, when the user uploads the source video, so the source video will be transcoded according to the ladder configuration into these multiple representations. So the ladder configuration is the input to the transcoding engine. And meanwhile, we have a ladder generator that based on many, many factors, including the video characteristics and some big data, to create this ladder configuration. So as I said, so the ABR algorithm, so there's a rich literature for that. The room for improvement is probably small, right? But for this research, we're gonna focus on how to generate the ladder. The room for improvement is unclear because there are much fewer work on the ladder generation. So basically, the question I want to answer is how to generate the optimal ladder to maximize the quality of experience for billions of users of TikTok. So why ladder matters? Let me give you some intuitions, right? So the first reason is that if you look at the network speed distribution across the globe, right? So some countries have very good network infrastructure, but some developing countries, the internet infrastructure is a little bit poor, right? So we have to use different ladders in different areas. For example, in the US, where the infrastructure is good, we can have a ladder with a higher resolutions. But in, for example, Africa, right? So we probably will have a ladder configuration with a lower qualities. The second reason is that if we look at different videos, their characteristics are also different, right? So here I show for two videos, one video is simple and the other video is complex in terms of the content, right? So the x-axis is the bitrate of the video, and the y-axis is the video quality. It's called a VMAF, right? So VMAF, so basically it's just a score in the range of 0 to 100. It characterizes the video quality, right? And basically for these two videos are all the same resolution, 1080p. And each dot, basically we can control the encoding parameters. Even for the same resolution, we can come up with different encoding parameters to balance the trade-off between bitrate and the video quality, right? You can see that for the simple video, we actually just only need to have a low bitrate to achieve a pretty high quality score, the VMAF score. But for the complex video, we really need to have a very high bitrate in order to achieve the same VMAF scores. If you look at other resolutions, I mean, the story is kind of similar, right? So the takeaway is that we should use different ladders for different videos with different content complexity. So the third reason why ladder matters is that we have limited transcoding resources, right? So if you enumerate all possible transcoding combinations, there are hundreds or even thousands of combinations. But transcoding the video into that many representations, they consume a lot of CPU and GPU powers, right? So typically online, we are only able to, due to limited compute resources, we are only able to transcode into less than 10 representations, right? So the takeaway is that we should strategically generate a small number of representations from a large number of candidates. Yes. Yes, actually, I'll talk about that shortly. Yeah, in the whole framework. Yes, yeah. Okay, now here comes a little bit the technical part, right? Let's try to formulate the problem into an optimization problem. So we have multiple candidate representations of a video. And the problem is we want to select a subset of them, select n representations to maximize the quality of experience, right? So basically, the three things basically says the output ladder should be a subset of the input or input candidates. So the number of representations in the ladder is n. And this one basically says we want to try to search for all combinations of the representations and pick the one that maximizes the quality of experience. So then how to define the quality of experience? We use a very simple metric, right? So obviously we need to look at the quality, right? So the higher quality is, the higher QE is. And also we give penalty. Whenever it incurs buffer, rebuffer, or stalls, we give some penalty. And also the third term, well, we also give penalty on the data usage, right? Because if you have a higher bitrate, then we need to pay more to the CDN. And meanwhile, the end users will also spend more data, right? Whenever, for example, the user is on cellular network, right? So we also give penalty for the data usage. Okay, now how to solve this optimization? Remember that, so this optimization is invoked for each video. For each video, we want to, we basically call this algorithm to determine the best combination, right? So obviously we can do brute force, right? By search for all possible combinations, but this is too expensive. It incurs exponential complexity. So we use a technique called dynamic programming. You only need to know that this is like a more smarter way to search for the optimality, right? So it can have provable optimality, and it's much, much faster than brute force search because it has this so-called polynomial complexity. So the next question is how to calculate this QE, right? Remember, what is the QE? So this QE is that if this video is encoded by this candidate letter, what is the quality of experience on all users in the target region? So we find that this QE, remember we have this formula, right? So the quality is a positive factor, and we give penalty by rebuffering and the bitrate. So we find that it is really difficult to, for example, build a mathematical model to calculate the QE, right? Instead, we leverage the big data because we have billions of users' data, playback statistics. We just estimate this QE using big data. But I want to emphasize that we don't use any personal data. We only use anonymized aggregated data from the users. Okay, so now, so this is probably the most complex slide, right? So I'll use some animation to illustrate how we estimate the QE using the big data. Remember, so there are three components, right? Quality, rebuffering, and bitrate. I'm only gonna explain how we estimate this part, the quality part, right? The other two components are conceptually similar. Okay, so the idea is that we want to, remember we use this VMAF, right? It's a score to estimate the quality, right? So the quality metric basically want to calculate the average VMAF score across all the representations, and each representation, the quality should be weighted by the viewing probability of each representations, right? So keep that in mind. So we use this formula to estimate the quality, right? So first, we need to have this VMAF score, right? So basically, we have a lightweight machine learning model that try to predict for each representation's VMAF score and the bitrate without performing actual encoding, right? So here, these three numbers are the predicted VMAF score. It actually encompasses the complexity information of the video. And also we predict the bitrate, right? So this is the VMAF prediction part. So then we need to calculate the weight, right? We need to consider for each representation, what is the watching probability? So the watching probability depends on many factors, in particular the network speed, right? Because different network speed, we have different viewers. And under different network speed, the watching probability of a representation will be different, right? So what we did is that we used our big data. We have the network speed distribution, right? Then we discretize this. And for each network speed slot, right? So this basically this I in the summation goes through all the network speed bin. And the PI is basically the probability of the play frequency of this network speed, right? So this is PI. So then within this network speed bin, we try to also use big data to plot the video bitrate distribution. And this Qij is basically the play probability of the J's representation in the I's network speed bin, right? If you multiply Pi and Qij, it's basically the viewing probability of this representation in this network speed bin and this representation, right? So then when we have this representation, remember we have the predicted bitrate, right? We just plug this play bitrate prediction into the distribution and use that to calculate Qij, right? So the idea is also not very difficult, right? For example, in this ladder, we have three representations. If the bitrate is less than R2, then we basically pick the lowest level. If the bitrate is between R2 and R3, we use the middle level. And if the bitrate is higher than R3, we use the highest level. Yeah. And lastly, we try to rewrite this as a matrix multiplication to speed up the calculation. It can speed up by 10 times. Yeah, I understand this slide is a little bit crowded, but I just want to let you try to appreciate the technical depths of what we do every day. Yeah. Never mind. Yes. Yes.
Are there instances where, like, if the source video has like lower bitrate or lower quality, you're kind of experiencing some shortage in those candidates?
Yes, yes. Yeah. If the source video has a low quality, we'll apply some threshold, yeah, to also to limit the transcoding resolution. Yes.
Okay, but at the end of the day, you would still have those candidates that you can apply all the
Yes. Yeah. Yeah.
algorithms
We
for.
do consider the resolution of the source video. Yes.
No, okay. Thank you.
Okay. Yeah. Oh, that is because remember we have this ABR, right? So ABR algorithm will determine the quality based on the network speed. Yes, basically I think there are two things. One is our recommendation system, right? So that recommendation system basically determines which content to provide. So then our algorithm just assume that the recommendation is already done. So then given this particular video, right, we already know that we're gonna play this video. Then we have multiple qualities. Then to pick which quality determines is depend on the network condition. Yeah, all right. Okay, now let me give you the big picture, right? So remember we have this optimizer, which try to solve this optimization problem to come up with a ladder, right? And in order to calculate this QE, so this optimizer will give the candidate ladder to a simulator, which calculates this QE function, right? And the simulator will give the calculated QE to the optimizer, and the optimizer will produce the optimal ladder and give that to the transcoding engine. And then for source video, so it will be transcoded according to the ladder to multiple transcoded representations. And these representations will be consumed by the clients. And meanwhile, remember we use a big data driven approach, right? So these client players will also upload some data, some playback feedback data like network speed, rebuffering, bitrate. And these data will be processed at our data lake. And the data lake will provide such big data to the simulator to produce the QE metric. And also we have a video analyzer, which try to predict the VMAF and the bit rates, which are also used by the simulator for QE calculation. Yeah. Yeah, when the video, so first for this part, so this T ladder, so when a video is uploaded, it needs to be transcoded. So this function is invoked to determine the ladder. Yeah. Okay. So now let's talk about the evaluation. I'll finish in 3 minutes. So we implement this in TikTok production system. It was launched in 2024. And we do A/B test in global scale. So the base group is called a V-ladder. So V-ladder is our legacy laddering system. And we compare it with T-ladder, which is a control group, right? So here are some key differences between the V-ladder and T-ladder. So first, V-ladder performs just a brute force search. Because of the limitation of the brute force search, we can only have the ladder configuration in a per region basis. Basically, in the entire region, it uses the same ladder configuration. But for T-ladder, because it performs this dynamic programming, it's much more efficient. So we can do per video laddering. And also T-ladder, as I said, so it leverages the playback feedback from billions of users, but V-ladder doesn't do that. So we pick 2 regions for evaluation. That's the developed region and the developing region. So you can see that they have a huge number of users, DAUs. And now, so this is the result for developing region, right? We look at multiple metrics. First, the QE. The second is the VMAF, which is the video quality, and the rebuffering and the CDN cost, right? You can see that for our new system, T-ladder, it simultaneously improves all these, at least the first 3 dimensions, and incurs similar CDN cost. Okay, let me try to summarize, right? So first, I hope this you will be convinced that so the ladder, it determines the ABR's solution space. And bitrate ladder optimization is really important. It is as important as ABR or even more important than ABR, right? Why? Because as I demonstrated, so there are region diversity. We need different ladders for different regions. there is video diversity. We need to have different ladder for different videos. And also we have limited transcoding cost. Yeah. Yes. So we do have a also a component which I didn't have time to cover. We try to predict like the popularity of the video. So depending on the popularity, we have different streaming strategies, including this transcoding strategy. Yeah, but I just didn't have much time to talk about such details. Yeah, we do consider the popularity of the videos. Yeah. And also, yeah, go ahead. Mm-hmm. So again, so that's the problem. So there are two orthogonal things, right? One is the recommendation system, which determines which content to be streamed to the users. And our team just treats the recommendation system as a black box, right? And our team's responsibility is to determine, given this video, we already determined that the user is gonna watch this video, what kind of quality we pick, right? So these are like two orthogonal problems. Our team deal with the second. Yeah, to be honest, I don't have much, know much details about recommendations. It is a really complicated system, yes. Yeah. And the last point probably is the, another key takeaway is that we demonstrate that using billions of users playback data, in addition to the video content information, is really essential to ladder construction or any streaming strategy in general, right? It can help simultaneously improve the video quality and the playback smoothness. Okay, so I'll stop here. Thank you very much.